Today we are going to discuss our second part of the MCQ discussion of evaluation test 2. So last week we discussed from MCQs from 1 to 10, right? I hope you remember we did a very lengthy discussion that almost took 3 hours. But that actually worth, isn't it? So we discussed in depth about each theory part we can see in that paper. Okay, so today we're going to continue the second part of that discussion. So right, let's start from the 11th MCQ. Okay, so it is coming from chemical calculations. Okay, so let's read the question quickly. In a reaction used for the industrial manufacture of titanium, right, 285 grams of titanium chloride and 96 grams of magnesium were allowed to react. Okay, so you can see those are the reactants. What are the reactants? TiCl4 and magnesium. And in this reaction, magnesium chloride and titanium were produced. Okay, so you can see nicely in that statement, they are telling about the reactants and products. Okay, so then since it is a calculation question, obviously we need a balanced chemical reaction. Okay, so first of all, before doing anything, what we need this reaction to be balanced. Okay, so since we identified the reactants and products, we can start from there. Okay, so if I talk about overall chemical calculation, MCQs and essay structured questions, okay, so they always gives, most of the time, they gives a chemical reaction. Okay, so then if you know the products and reactants, you have to balance that one before doing anything. Understood? Because once you balance, you might remember there is a number coming in front of reactants and products. So we call that one as stoichiometric coefficient. Okay, so that is representing the molar ratios of the reaction. Okay, so let's do this balancing first of all, and let's talk about a little bit about that stoichiometric coefficient and its use. Okay, so I think it is a good start for the calculation MCQs. Okay, so now let's try that one. So what are the reactants? TiCl4 and magnesium. And the products will be titanium metal and magnesium chloride. Right, so like I said, we need to balance this one. So balancing means, in the left side you have reactants, in the right side you have products. No? So the number of atoms available in each side should be the same. Okay, so if I tell you, now you can see here, only one titanium atom is there, element titanium, here only one is there. Okay, so the other side also should have one. So that is satisfied, no? In the sense of titanium, this reaction is balanced. But check, what about chlorine? Here you have 4 chlorine atoms, right? But in the right side, you have only 2 chlorine atoms. That means it is not balanced. So first thing you should do is balancing that. Okay, so to balance this chlorine, what should we do? We have to add 2 in front of this magnesium chloride. Then if you think about this compound, it is 2 times magnesium chloride. That means there are 4 chlorine atoms. Understood? Now it is balanced in the terms of chlorine. Okay, so this is what we call as the inspection method, this balancing. Remember, in O levels also you use this one, right? Here we are balancing this chemical equation using inspection method. Understood? So like that, we now balanced chlorine, but there is a still problem, right? You can see magnesium is now not balanced. Okay, so now in this side you have only 1 magnesium, but in the other side you have 2 magnesium atoms. So what should we do? Put 2 in front of this magnesium. Understood? Now this is a balanced chemical equation. Okay, so this is what we call as, like I said, balancing using inspection method. Okay, so what is stoichiometry? What is stoichiometry ratio? Okay, for this equation, you can see there's nothing in front of TiCl4. Okay, so if there's no number, that means the number is 1. Understood? So here 1, 2, then you have again 1 and 2. So this is what we call as the stoichiometry ratio. It represents how this reaction occurs when these reactants and product reactants are added. Okay, so example, if it is 1:2, that means what? 1 mole of this one can react with 2 moles of this one. Can you understand? 1 mole of this reacts with 2 moles of the magnesium. Okay. So then if you take, let's say, x moles of this one, then 2x of magnesium should react with that. Understood? Then the other side also you can relate to that one. So if here x moles of TiCl4 and 2x moles of magnesium are added, right, you will get x moles of Ti and 2x moles of magnesium chloride. Understood? So that is what we call as the stoichiometry ratio. And if you consider chemical calculation questions, balancing this chemical reaction is a very important thing. And this question given as the 11th MCQ, okay, so kind of a challenge is given for you. They haven't given you the chemical reaction, right? So they just gave that as a statement. You have to figure out what are the reactants and products. Okay, so now I think it is clear to you. Now let's focus on the given data. Okay, you can see it is telling you TiCl4 285 grams are there. So from this reactant, 285 grams available. From magnesium, it is telling 96 grams are available. So these are the masses of TiCl4 and magnesium. Okay. Now, then again they are telling 36 grams of titanium is produced. 36 grams is produced. 36 grams of titanium is produced. Okay. Right. Now what they are asking is percentage yield. So let me talk about percentage yield for a second. Okay. So it's something like this. Now our target here is to make or produce titanium. Right. So what we expect here, right? When these amounts are reacted, let's say 1 mole and 2 moles are reacted, we are expecting to have 1 mole of titanium. That is the expected yield. We call it as the yield. Okay, expected amount. Okay, expected. We are expecting 1 mole of titanium. But the problem is in real life, okay, in real chemical, reactions and industries. So what we expect is always not happening, right? So for example, if we expect 1 mole of titanium here, okay, so actually it may give less than 1 mole of titanium. So that's the real nature, okay, because there are problems with the chemical processing and chemical reaction that is happening. So it can give a lesser amount than we expected. Okay, so then how do we express that one? Okay, so for example, let's take about an exam. That's a common example I'm taking in your class, right? Let's say there is a test. So take, for example, this test. So there were 30 MCQs, right? So what we are expecting is for you to get 30 out of 30, right? That is the expected amount. But let's say there is a student who is getting, right, only 15 of the questions right. Understood? So then the actually obtained marks is 50. So how do we put that one as a percentage? Okay, so how do we put that one as a percentage? So we expected 30, but that student got 15 MCQs right. Okay, so this is the expected amount, and this is the actual amount. Okay, so how do we put it as a percentage? 15 over 30 into 100%. So then you will get 50%. So we can say 50% is the yield, percentage yield, something like that. Here also, how do you get the percentage yield of titanium? So you are expecting, you have to say expected titanium mass. You have to find expected titanium mass, and you have to put in the numerator actual titanium mass, which is given here, 36, right? And then you have to make it as a percentage, make that fraction as a percentage. Understood? So to find the percentage yield of this reaction, so that's the second thing you need to understand. First thing is balancing. Okay, balancing the reaction and what is meant by this stoichiometry ratio. That's the first thing. Okay, and the second thing is what they're asking in this question is percentage yield. No, so without understanding this, there's no point of even trying this question. Okay, so what they are asking is percentage. Okay, so meaning of the percentage yield is this one. So you are expecting some amount which you don't know here. You need to find this one using the calculation, right? And they have given you the actual amount, 36 grams. Okay, and then find this percentage yield. Understood? So that is the second thing you need to understand. Right? So I hope it is very much clear to you. Now let's see how to find this expected amount of titanium, expected mass of titanium. Okay, so you have been given added amount of TiCl4 and magnesium. Right, so then don't do anything like, you can't add them, subtract them. Those are not going to work. Because Ramai, a reaction is happening according to their molar ratios, stoichiometry ratios, isn't it? So, like I said earlier, 1 mole of TiCl4 is reacting with 2 moles of magnesium. You have to consider moles, not the mass. Okay, so don't do that mistake. Okay, so I'm talking from a very low level. Okay, understand? So then everyone can understand this discussion. Okay, so first of all, you need to find these moles of each compound. Understand? After finding moles, you can use this ratio and do the next steps. Understood? So the third thing you need to understand, first thing is balancing the reaction. I hope it is very much clear to you. And the second thing is understanding what is this percentage, what they are asking. And the third thing is this equation and these ratios are working for the moles, no? Right? So they haven't given moles, no? They have given only masses. So the next thing you should do, the third thing, finding the moles of these added things. Understood? So now let's do that one. Okay, so like I'm telling here, there are several steps in this calculation. Understood? So if you are not comfortable with calculations and questions and all, you have to focus here and repeat these steps after the class also. Okay, so when you are writing the review, okay, pay attention to those points and practice the same question again and again and again until you get it right. So until you are able to teach this one for someone. Understand? Then we can be sure about, okay, now I can do this calculation like that. Understood? So then you can practice few more questions and see. Okay, so that's the only way to get the calculation theories right. Okay, so in your A-level exam, there will be nearly 3-4 calculation MCQs which you can't skip anyway, right? So one MCQ means 1 mark. So even those 4 marks matters for your Z score. Understand? So I don't need to tell you the importance again and again, so you know it, right? So my advice is, right? So follow these steps. Okay, so I know there are students who can do this really well, right? So very good, but still as a class, we need to move forward as one class. Understood? So that's why I'm telling this one. So the next step, like I said, the third step is what? Finding the number of moles of these two reactants. Okay, now let's do that one. Right, to find number of moles, there are several equations. So we are using here mass over molar mass formula, which you learn even in O levels, right? Because they have given the masses. No? So we need this molar mass. So molar mass of TiCl4 and molar mass of magnesium, right? Now let's check our question. They should give us the molar masses. So the relative atomic masses, you can see here within a bracket, they are giving that one. Titanium, relative atomic mass is 48. Okay, right. Now let's find it. TiCl4, molar mass of TiCl4. How do you find it? Titanium 48. Chlorine 35.5. So there are 4 chlorine atoms. No? So you have to multiply that one by 4. Right? And let's do the math here. 35.5 into 2 is 71. 71 times 2 is 142. 142 plus 48, 0, and 190. Understood? 190. 190 grams per mole. So now, how do we find titanium moles of titanium chloride? So we are dividing this 285 grams by 190 grams per mole. 190 grams per mole. Okay, 190 grams per mole. That is the way you are finding the number of moles. Right, so now we need to try this division. 285 is divided by 19, 28.5. So there's only one. So 19. So then you're left with another 9. 95, you have 2. For 95, so 95 you have 5 of 19s because 190 half is 95. Okay, so then this is the answer. 1.5. 1.5. So you have 1.5 moles. 1.5 moles of TiCl4. Understood? So then repeat the same thing for the magnesium. Magnesium relative atomic mass is 24, so its molar mass will be 24 grams per mole. Okay, so now let's find out moles of magnesium, which is 96 grams division 24 grams per mole. So it's given how much? 24 times 2 is 48, 48 times 2 is 96. So it's 4 moles. So like this, we have to find the moles of each reactant. Okay, so finding moles of titanium is not necessary. Don't try that one because as the second point I established, what is the use of this 36 grams? It is there to find percentage. So no point of converting that one again to moles. Yeah, right now, no need, right? The method I am going, I don't need the moles of titanium because why? Because I'm going to find anyway the expected mass of titanium. So for my method, I don't need the moles of titanium. Okay, so let's see how it is going there. Okay, right. Now you can see the two reactants are there. Okay, so I'm not sure whether which one is fully reacting. You understand? So now I'm going to come to the fourth point here. Okay, so there are two reactants. So I'm not sure about which one is fully reactive. Okay, so now you can see in this ratio with 1 mole of TiCl4, 2 moles of magnesium are reactive. So if I added 1.5, okay, so let's say if I added 1.5 moles, right? So how much of magnesium should react with that one? 2 times like that, no? That means 3.0 moles of magnesium should react with that. Okay, so if I added 1.5. So, but if I added 4 moles of magnesium, half of that one, that means 2 moles of titanium chloride should react with that one. Understand? So like that, you can see the numbers are different. Right now, take this example. If you added 1 mole of titanium chloride and 2 moles of magnesium here, they both will fully react, no problem. But in this question, you can see the added moles are not matching. Okay, so if I added TiCl for 1.5, only 3 moles of magnesium will react with that one. But if I added 4 moles of magnesium, like it is telling here, only 2 moles are reacting with that one. So it's not matching. Okay, so then you need to understand which reactant is fully consumed. Okay, even though there are 2 reactants, only one is going to be fully consumed. Okay, so which one is going to be? So now let's take this one. So when I added 1.5 of TiCl4, only 3 moles are reacting with this one. Only 3 moles of magnesium is reacting. Right? But I have added 4 moles of magnesium. That means I have added magnesium excess. Can you understand? So the fully reacting one will be what? TiCl4. Okay. Can you understand that one? So you have to write this as a statement in your review. Okay. You have to write this as a statement. Okay. What you have to write is with 1.5 moles of TiCl4. Okay. With 1.5 moles of TiCl4, only 3 moles of magnesium will react. Only 3 moles of magnesium will react. Okay, only 3 moles of magnesium will react. Okay, only 3 moles of magnesium will react, but we have added more than that. Okay, but we have added more than 3 moles. Okay, so therefore, TiCl4 is the limiting reactant. It is fully consumed. We call it as the limiting reactant. Okay, so now if you had a doubt regarding limiting reactant and related theories, now it should be a little bit clear, no, in this discussion, isn't it? Right, now you can say the same thing in terms of the second expression we wrote here. So you can say like this: to react with 4 moles of magnesium, you need TiCl for 2 moles, but you don't have that amount of TiCl4. Therefore, TiCl4 should be the limiting reactant, or the one that is fully consumed. Okay, so in that way you can understand. Okay, Lama. Now we know how much exactly reacted. How much exactly reacted. Okay. Right now, I didn't tell you that thing, right? So this is some separate topic we discussed in our theory discussion, isn't it? Under chemical calculation lesson, we discussed this one separately. What is that topic? What is that topic? ARR method. Remember, added, reacted, remaining method. Okay, limiting reactant. Oh, that's the whole idea. Okay, so when we do these questions in the class, I introduced you that ARR method. So I didn't use it here, okay, because I need you to explain in a different angle. So if there is a student who didn't understand ARR method, then he or she can understand. If he or she can understand this one, then still I can relate this one to ARR method later. Okay, so now that's what I'm going to do. I'll link this method to the ARR method. Okay, now I'm going to erase this mole finding thing. Okay, then let's write this ARR method. So again, we are taking this balanced chemical equation. TiCl4 reacts with 2 magnesium and to give 1 titanium and 2 magnesium chloride. Okay, so the ratios are 1:2. 1:2. And here we are writing added, reacted, and remain. Added, reacted, and remaining. So here, like I said, we are adding 1.5 moles of TiCl4 and 4 moles of magnesium. We haven't added anything from those are production, so there's nothing added at the beginning. So when the reacted one, now we know exactly this is the proper one, and this is not going to happen. Understood? So when you are trying the questions, try this method also. It's good. And then which one is fully reacting? 1.5 moles of TiCl4 is reacting, and with that 3 moles of magnesium are reacting. So to ensure that we understand it is reactant, we put a minus sign in front, because when we get the remaining row, we can simply subtract this. We can simply get the difference here. Okay, so 1.5 minus 1.5 is 0, so nothing left. So that's why we called earlier this as our limiting reactant. Limiting reactant. Understood? And this one here, only 4 reacted. So only 3 reacted. So 1.0 is remaining. Okay, and then you can use this same thing to find how much titanium we expected. Okay, so now you can see I'm linking it to the last point. Expected, we need the expected titanium mass, no? So now we are going to find expected titanium moles using this method. Okay, so if you reacted 1 with 2 of this one, you will get 1 and 2 of this one according to the ratios, as I explained earlier. So if you reacted only 1.5 titanium chloride, okay, so then 1.5 titanium will be released, will be produced, and here 3.0 will be produced. Understood? So the remaining ones also will be 1.5 and 3.0. So now you can see here 1.5 moles of titanium is expected by this process. Understood? That is how you are finding it. So now let's repeat again from the very first point. What was the first point? First point was balancing, identifying the reactants and products and balancing this chemical equation. That is the very first thing you need to do. And for that we used inspection method. Okay, and the second thing, second thing is they are asking in the question something called percentage yield. Okay, it's something very similar to the marks in a test, right? So, like I explained, if we need to find what we need to find the percentage yield, the expected amount and the actual amount. Okay, so actually it says you got 36 grams, and then you need to find how much grams of titanium are expected. That's the second point. Then you can multiply that from 100% and get it as a percentage. Okay, so like we express marks in a test. If there are 30 MCQs, if someone got 15 MCQs right, so his marks will be 50%. Okay, like that. Then the third point was these stoichiometry ratios are representing moles. Okay, so they are actually works only for the moles. So then they are given only the masses, no? So you need to find the moles of TiCl4 and magnesium. That's the third point. Then the fourth point is, you can see, right? The added amounts, one of the reactant will fully consume and other one will remain. So you can see that one by checking the moles. So to do that one, we are using ARR method. But today I explained that using just the moles here, right? So just understand with 1 mole, only 2 moles of magnesium will react. No? So if you add 1.5, only 3 moles of magnesium will react. So that means our 1.5 titanium chloride is the limiting reactant. Okay, so you have more than this magnesium. Okay, so therefore magnesium will be the excess reactant. You can represent that one using this ARR method. And please check. There are more questions in our theory notes and earlier paper classes. You can catch up this one up to a very good level using those questions. Okay, so try. Now today just understand if you miss this one. Okay, now still we are missing the last piece, okay, to our answer. So what is the last piece? Okay, so we got the expected moles, but for here we need the expected mass. So how do we combine this one, connect this one? To find mass, we are using moles into molar mass formula. So 1.5 moles are there. So molar mass of titanium is 48. So by multiplying these two, you can find the expected mass. Okay, so 72 grams are expected if you multiply. So then you can actually find this percentage yield. So you expected 72, but you got only 36. Okay, in grams. Then the percentage yield will be this is exactly half, no? So 50%. 50%. Understood? That is how you find the answer. So I hope this explanation is enough for anyone to understand and even recall the whole theory area regarding limiting reactants. So this is actually a shadow question of 2019 A-level MCQ. You can check that one. So you can write that too. This is a shadow question of 2019 A-level MCQ. As I remember, that MCQ may be 7th or 8th MCQ. I don't remember exactly, but maybe it is there. It was there within first 10 MCQs. So you can take your past paper book and do that MCQ also. Okay. So in that MCQ, they didn't ask the percentage yield, they asked something else. Right, so understand it. ARR method or limiting reactant, percentage yield, those are important theories. Okay, so at least understand in a single question, then repeat that one and try to teach that one for someone. Okay, it's the way you have to learn. Right, now we did the first MCQ for today's discussion, 11th MCQ. So answer is answer 2. I hope you all understood that really well. So if you have further questions, you can ask that one within the class. Okay, so when you are coming to our next week class, you must write these reviews and bring that one with you. Okay, because that's why I'm spending my time, right? Because I want you to get some benefit from that one. Okay, right, now let's go to the 12th MCQ. Look at that one. The molecule that can form only London forces as the only intermolecular interaction among molecules of same kind. Okay, right, now Now, here, so now earlier question we discussed about calculations. Now this question, they are asking about intermolecular interaction, intermolecular attraction. So that topic is there in your second unit, bonding. Okay, second unit bonding, you can find this topic. So I'll do a small explanation because in our last paper discussion, so MCQ 1 to 10 discussion, we kind of completed a great deal of this second unit. Okay, resonance, hybridization, and you can see here the hybridization question was the 10th question. So resonance question, right? Then VSC, PR theory, Lewis structures, bond angle, bond length, everything was covered, right? So what we didn't talk about that day is this one. What is intermolecular attractions or secondary interactions? Okay, so I will kind of revise that theory part quickly and then go to this question. Okay, right, so this is how it goes. So if you think about chemical bonds, there are two, we can classify that one into two main types. Okay, the first thing is you have primary interactions which carry a great strength, primary interactions. Then you have a little bit weaker secondary interactions. So primary interactions examples are covalent bonds, ionic bonds, which you learn in O levels, and in A levels you are learning another type of interaction which we call as metallic bonding. So those are kind of very strong bonds, covalent bonds. They are formed by sharing of electrons, right? So in A levels we call it as overlapping of atomic or hybrid orbitals, so which is very strong. Basically they kind of electron mediated, right? And then ionic bonding, it's an exchange of electron, right? Or in A levels we say positive negative ion or cation and ion attraction, which is also very strong, ionic bonds. Okay, and the third one is what? Metallic bonds. So that also are a very strong bond. So here the primary interactions are kind of stronger. Okay, and then there is something called secondary interaction, which are basically plus minus delta minus attractions. They are somewhat weaker. Okay, so for each secondary interaction, a molecule is involved. Okay, so there are 5 secondary interaction types. Okay, so what are those 5 secondary interactions? We have DP-DP, dipole-dipole interactions. Then we have DP-IDP. I'll explain what this means. And then we have IDP-IDP. IDP-IDP. Okay. Then the next two is ion DP and ion IDP. So now you can see dipole, DP, IDP, those things are there. So each one is representing molecules. So that's what I said. For secondary interactions, molecules are involved. Okay, molecules are involved. Right. So what is this DP-DP? Dipole-dipole. Example, HCl and another HCl molecule. So these two HCl molecules, you can see the covalent bond within here, which is a very strong bond. Okay, but secondary interaction is this one, the interaction that occur between the two molecules. It's not within the molecule. Okay, so the attractions occur between molecules. Okay, so this is what we call as the DP-DP, dipole-dipole interaction. So how this is occurring? I'm going to explain that. Okay, so now you can remember. Okay, so when you consider hydrogen and chlorine is more electronegative than hydrogen. Okay, so since it is more electronegative, electrons are more attracted towards chlorine. So chlorine electron density is higher, so which gives it a slightly negative charge because it is having more electrons. Okay, and then hydrogen electron density is lower, so it is having a slightly positive charge. So like that, here also delta positive and negative there. And now you can understand how this attraction is occurring. It is an attraction between slightly charged or polarized, we call this is as polarized, two molecules. Okay, So we call this molecule as a polar molecule because it has a permanent, so this has a permanent dipole. Permanent dipole. Permanent dipole means it is always there. Okay, so there is something, then if there is something permanent, then there should be something temporary, no? Okay, that's why it is coming. So I'll explain what is temporary in a minute, right? So here this attraction is occurring between permanent polarized dipole and permanent polarized dipole. So dipole means two poles are there. So that's a simple idea. Okay, simple idea. So polar molecules will form what? These dipole-dipole interactions, dp-dp interactions. So what is dp-idp? There are molecules like, let's say hydrogen. Okay, so these molecules are kind of symmetric, and you don't have any extra electron place. That means there's no high electron density, so they both kind of symmetrical. Okay, they both kind of symmetrical. But when this molecule approximates to a polar molecule, like this, okay, so its electron cloud will begin to change. So now let's say this is the permanently polarized one. So then these electrons that are existing here can repel these electrons. Here also you have electrons, but the thing was earlier this electron cloud was symmetrical. Okay, so they will repel, this negative charge will repel these electrons. And there will be a temporary dipole produced, a temporary one. This occurred because of this polar molecule. Understood? So then they can make an interaction. This is what we call as what? dp-idp interaction. Okay, so we have the dp dipole here, and here you have the idp. So what is this I stands for? I stands for induced. So you can call this process as induction. Induced dipole. Induced dipole. Understood. So then originally we call this one as a non-polar molecule. And here non-polar molecules and polar molecules are making this induced dipole interaction. Okay, so this non-polar molecule will be temporarily polarized due to the influence of the polar molecule. That's a simple idea. Okay, so now you can understand about these two interactions well. Okay, so dp-dp interactions will occur between polar molecules. dp-idp interactions will occur between non-polar, polar and non-polar molecules, like this. Okay, so you can give more examples here, right? Not only HCl and H2. You can think about this one. You have heard that oxygen. Okay, oxygen is a non-polar gas, O2. But oxygen is able to dissolve in water. Okay, then only aquatic organisms can, breathe, or they can fulfill their oxygen requirement. So that means at least a small amount of O2 is dissolving in water. Water is a polar molecule, just like this. And O2 is a non-polar molecule. So when oxygen gas and other non-polar gases are dissolving in water, they are making dp-idp interactions. Can understand that? When those gases are dissolving in water, they make dp-idp interactions. Okay, so like that, there are examples. Okay. Then go to the third one. Dipole-induced dipole. Dipole-induced dipole. Now, I explained you what is meant by induction. So for induction, something already polarized should be there. Okay. But they are explaining there is a possibility of happening what I'm going to say now. Okay. Now take this H2 molecule, for example. It doesn't have any dipole, but from unit 1 you understood electrons are kind of very uncertain, so they can move around. It's not a rigid structure. It can basically move here and there, those electrons. So it says there can be a chance due to these random electron movements. There can be a chance that a self-induced dipole self-induced dipole can occur due to these random electron movements. Okay, so because electrons are moving, as a reason of that, okay, there can be a, a, a self-induced dipole for at least for a second. For a minute time, it will be formed. At the next moment, it will not be there. Okay, but due to this electron movement, this can happen. Okay, it's not going to be a permanent one. In the next moment, like I said, it may not be there. Okay, so but still self-induced dipoles can occur within non-polar molecules without any external support. Understood? So then if this self-induced dipole can induce another molecule, now let's say there's another non-polar molecule nearby, so this one can induce that molecule also. So then that molecule's electron cloud will also be changed. Now can you understand? So as a result, there will be interactions between what? Non-polar and non-polar molecules. Okay, so that is what they call as IDP, induced dipole and induced dipole interaction. So this induction starts from a self-induced dipole. Okay, so IDP, and there's another name for this one. This is what we call as London forces. You might wonder, right? In that question, London forces were there, but it wasn't mentioned here. So London forces is what? IDP. And the important thing is, okay, so the next point is London forces can occur between any two molecules. Okay, so what that means? So I earlier explained this is happening within non-polar molecules. Okay, so for non-polar molecules, London forces or IDP is the only attraction they have. There's nothing else because they can only do this one. But this self-induction and others can happen in polar molecules also. Okay, because polar molecule electron cloud is also moving now a little bit, isn't it? So then there can be a chance of having this kind of a molecule. The permanent dipole is there. This is the permanent dipole. And there can be a temporary dipoles also. Just like this. Can you understand? This is a temporary dipole. So because of this temporary dipole, it can again undergo self-induction and all. They can form IDP, induced dipole and induced dipole interactions. Understood? So the idea is this is just a diagram for you to understand. Okay. So there's not, you can't say like this, but it's just a diagram for you to understand. Just know, okay, induced dipole interactions, okay, can occur, or London forces can occur between any type of molecule. Okay, so it is the only interaction for non-polar molecules, and polar molecules can also form London forces. Okay, so now if you think about the possibilities, there are three possibilities now. So what is going to be there between non-polar and non-polar molecules? It is only London forces. Okay, then what is going to be there between polar and polar molecules? Polar, it is going to be DP, then London. Okay, and then between polar and non-polar molecules, you can have DP and London, like that. Okay, so London is a common intermolecular attraction. Okay, so I didn't talk about these two. Okay, so you can refer our theory note or the theory recording just to remind this. If there was a question in this paper, I'm going to explain it anyway. And there is another thing I omitted from our discussion. There is a special dipole-dipole interaction called, special one called H bonds, hydrogen bonds. Okay, so there are questions in this paper. I remember one was there in the true false last 10 MCQs. When I'm discussing that, I'll explain about hydrogen bonds too. Okay, so right now, understand about these three. Okay, these three. Okay, so if you understand what I said now, then it is enough for do this question really well. So now you know where this theory is stated, no? Okay, now let's jump into the theory part. The question, sorry. Okay, in the question, you can see It's asking the molecule that can form only London forces as the only intermolecular interaction among molecules of the same kind. So they are asking only London forces. That means now you have to understand it. Okay. If there are molecules that can form only London forces, that means those molecules must be what? Those molecules must be non-polar molecules. Can you understand? That molecule must be non-polar because only non-polar molecules form London forces, only London forces. Okay, so non-polar molecules are the ones that are forming only London forces because non-polar molecules don't have any other intermolecular attraction. Because non-polar molecules and non-polar molecules can't form DP-DP, like I explained now. Okay, so now it is simply asking what? If you put this question into other words, what they're asking? They're asking which one of the following is the non-polar molecule. So shall we write that one? Which one of the given 5 is non-polar? That's what they're asking. Okay, so which one of the given 5 molecules is non-polar? If you can find that non-polar molecule, it is the one that going to form London forces only. If you can find that non-polar molecule, that is the one that going to form London forces only. Okay, so now examine these 5 molecules and find that. That's the thing. Okay, so in order to find whether it is polar or non-polar, right? You need its Lewis structure. Then you need its geometry. Then you need to address and you need to mark the dipole moment. Then that's how you identify the polar non-polar molecules. Okay, I'm going to explain that too. Okay, let's start from this simple molecule. So there are 5 molecules. Give me a second to write them in the board. H2O2. Then you have COCl2, CO, and SF4. Then you have XeF4. Okay, so now let's start from carbon monoxide. Lewis structure of carbon monoxide is this. Lewis structure. Now you can see it's a simple diatomic molecule. And it's not going to be non-polar because oxygen is more electronegative. So this is a polar molecule. Polar molecule. Okay, so it can form DP-DP and London. It's not forming only London forces. Okay, between 2 carbon monoxide molecules, there will be London forces and dipole both. Right? And then take this one. COCl2. So now to examine whether this one is polar or non-polar, you need to mark the dipole moments. So chlorine is more electronegative. In the last week discussion, I explained you the dipole moment. I hope you remember. It is simply an arrow that you draw from less electronegative atom to more electronegative atom. You can see here, chlorine is more electronegative than carbon. So then you put an arrow like this. That's how you do it, okay? Right, now you have to understand whether they are cancelled. So now these arrows are not going to cancel. Okay, let me show you one that is going to cancel, then you will understand it more. Take BF3. This is also the trigonal planar molecule. And if you draw these dipole moments, okay, you are considering them as vectors. You know, vector addition. If there are 3 vectors with equal magnitudes in 120 angle to each other, in physics, you understand, they are going to cancel. The resultant will be 0. Resultant is 0. So just like that, our dipole moment is also a vector quantity. So if it is a trigonal planar one, that means 120 angle to each other one. And if the magnitudes are also same, then it is going to be cancelled. So this is a non-polar molecule. Non-polar molecule. So dipole moment we indicate by the sign mu. So mu resultant is 0, mu r 0. That's what we wrote. But here, the mu r or resultant dipole moment is not going to be 0. Why? because the dipole moments are not equal, even though they are arranged in 120 angle to each other. Okay, so this is again a polar molecule, just like carbon monoxide. It will form DP and London both. Can you understand that? Okay, then come to this one, H2O2. After drawing the structure, you will understand this is also going to be a polar molecule. Okay, so about H2O2, you will learn further under inorganic chemistry. So you will understand a little bit more about H2O2. Right now, just understand this is how it look like. So when you mark dipole moments, it's going to get cancelled. Sorry, this should be the other. Yeah. It's going to get cancelled. It's not going to get cancelled. Okay, so it's a polar molecule. H2O2 is a polar molecule. Okay, then come to this SF4. So H2O2, you might not understand this one fully. So put a question mark and leave it, because under inorganic chemistry, you need to discuss this separate. Simply, it is this anyway. I'll tell. So this molecule is there in two planes. So this is one plane, and this is the other plane, or you can simply say this is the other plane. So that's why I draw the hydrogen like that. Okay, so it's like an open laptop, half open laptop, like that, or a book or something. So the molecule is there in two planes. So this is there in one plane, and this is there in another plane. So actually it's from here, will be there in another plane through the oxygen bond. Okay, so they are in two planes like this, so dipole moments are not going to get cancelled. That's how it is occurring. Okay, so then SF4. If you draw SF4 molecule, it is a seesaw shaped molecule as a lone pair. So then you can easily understand if it is, let's say, if it is PCl, PF4 or something, PF5 or something, it is going to be nonpolar because all the bonds are fluorine. Okay, so then this is nonpolar. Okay, but this one is going to be polar because this is the lone pair is exerting a small dipole moment which is not going to be cancelled. Which is, I mean, the resultant is not going to be cancelled. So this is also a polar molecule. So what should be our answer? Answer should be the last one. So now let's draw that molecule HCF4 and show how it becomes a non-polar one. So I'm not telling here about the Lewis method and the BSc-PR theory because everything we discussed in the last paper discussion. So anyone can understand by referring that video. So please do that one. So I'm not going to take time for that here. Okay, now this is actually a square planar molecule. Square planar molecule. And now you can see these four fluorine atoms are 90-degree angle to each other. So their dipole moments are cancelling. Okay, and here also there is a small dipole moment occurring from the lone pair. That is also going to get cancelled. So this molecule is a non-polar molecule. So non-polar molecule. So you have to identify that non-polar molecule. That is the one only forms London forces. Okay, so you need to understand it really well. This is an exam level MCQ. Okay, so what is the method of finding the answer? What is the method? First of all, remind about London forces. You need to understand what is a London force. So London force is simply an interaction that can occur between basically any molecule. But if they ask which one has only London forces, that must be non-polar molecule. It must be a non-polar molecule. So you need to understand this question is simply asking which of the following is the non-polar molecule. Okay. So to identify non-polar molecule, you need to quickly get their structures and mark their dipole moments. Okay, within your head, you can do this one and find what is having totally cancelled dipole moments. So I said earlier, these are vectors. You are simply doing here vector addition and see. Okay, so all these four molecules are polar. So they will form DP and London both, right? But this one is non-polar. So this can only form London or IDP only. Okay, it can't form dipole interactions. Understood that fully, Lama? I did the lengthy explanation about that. Okay, so that's it about the 12th MCQ. So write a good review, okay? Write a good review. So everything you can fix, okay? Don't worry. Don't worry. As I advised you during the classes, please do this one, then little by little, then face the monthly test coming from this January. Okay, little by little, you will get improved, okay? Don't worry. Okay. So there's another chemical calculation, but give me a second. Right, now let's discuss the 13th MCQ, which is asking another chemical calculation. Okay, so look at the question. A titration of 5 cubic centimeter of an aqueous sodium hydroxide solution of density 1.1 gram per cubic centimeter required 5.5 cubic centimeter volume of this concentration 1 into 10 to the power minus 3 HCl. Find the composition of sodium hydroxide solution in ppm. So it's a very good question. I mean, it's not difficult, but most of the students are afraid of pp. Okay, so I'm going to explain that fully. So you can easily you'll be able to understand this ppm and everything with this single question. Okay, so trust me and listen to this one really well and write a good review. Okay, now let's see how it goes. First of all, we need a diagram. So it's a titration between sodium hydroxide and HCl. Sodium hydroxide and HCl. So let's put sodium hydroxide into this flask. Okay, NaOH. So it says few data about this sodium hydroxide solution, which is it is having 5 cubic centimeter volume and its density is 1.1 gram per cubic centimeter. Okay, so that's it. And then they have given relative atomic masses also. Probably we need the molar mass of sodium hydroxide. I'll show you how to get that one. And then it is titrated with HCl. So don't worry about the word titration, right? It's just a simply it's a laboratory method which we use to properly react to reacting species. Okay, so don't worry about that one. We will discuss that under a different question, but let's focus what is happening here, right? So simply here HCl and sodium hydroxide are reacting. So understand that one. Okay. So about the HCl solution, it says from HCl 5.5 cubic centimeters are used and its concentration is 1 into 10 to the power minus 3 moles per decimeter cube. Okay, so we know the concentration and volume. So they're asking the composition of sodium hydroxide solution in ppm. So now let's see how to do that. So this is the volume and this is the concentration. Okay, the concentration. So what we can start from this question is, okay, so I remember the first question we did today. It's also a chemical calculation. So what was my first advice? I understand the reactants and products, then make sure that is balanced. If it is not balanced, then use infection method and balance it. That was my advice. Okay. So here also there is a chemical reaction occurring between HCl and sodium hydroxide, which you know it has an acid-base reaction. Okay, this is the acid, this is the base. So acid-base reaction is happening. And you know again, after an acid-base reaction, a salt and water are formed. Okay, so that is the chemical reaction happening here. So HCl is reacting with sodium hydroxide to form sodium chloride and water. Sodium chloride and water. Okay, so this is the balance reaction, acid-base reaction. Okay, so there are more kind of a little bit advanced acid-base reaction. So, for example, if you react sodium hydroxide with sulfuric, okay, ready? Sodium hydroxide with sulfuric, then 2 of the sodium hydroxide will react with 1 sulfuric because here it is releasing 2H plus. No? So to combine with this 2H plus, you will be needing 2 OH minuses. So therefore you need to put 2 in front of this one when you are doing the balancing. And the salt will be sodium sulfate, Na2SO4, and 2 water will be formed. Okay, so here the stoichiometry ratio will be 1:2, but that's a kind of an advanced step. I mean, not that advanced, but upper step, right? But even in this question, even they didn't check that. Okay, because we are focusing more on ppm. So other steps must be easy in order to check your knowledge about pp. That's why this question is designed in this way. Okay, so anyway, here the ratio is 1:1. Okay, it's already balanced. That's my point. Okay, so we are using that ratio. Okay, so that was the first advice that I gave in earlier question. Now, what was the second one? Because these ratios are only working for moles, no? Like I said, these ratios are only working for moles. So then you need to find out moles given in this question. So, but if you think about sodium hydroxide, the data is not that actually enough because it's not given, right? Moles, this data is not enough. But anyway, if you think about HCl, the given data will help you to find number of moles. So how do we do that one? Because there is another number of mole finding formula called C equal NV. So C equal N over V, or you can say simply N equals CV. Concentration is moles over volume. So therefore moles will be concentration into volume. So they have given HCl concentration and HCl volume. So let's multiply them and find the number of moles. Okay, understand? So moles of HCl will be what? Concentration 1 into 10 to the power minus 3 moles per decimeter cube. And volume is 5.5. But there is a small problem now, right? The volume is given in centimeter cube. Okay, but you can see concentration is expressed for decimeter cube. Now, when you multiply these two, unit must be cancelled. No? Then only you will get answer in moles. Okay, that means the per decimeter cube of this one should be cancelled by a decimeter cube volume. But the volume is given in centimeter cube. No? So, what should we do? We must convert this centimeter cube volume into decimeter cube volume. Then only it will get cancelled. Get the idea? Okay. So, 5.5 into 10 to the power minus 3 decimeter cube. So, how do we convert centimeter cube into decimeter cube? Like I explained here, like I wrote here, you are just dividing it by 1000. Okay, so simply remind in O levels, how did you convert milliliters into liters? How did you convert? You divided milliliters by 1000. Let's say you have 500 milliliters. Okay, so how many liters are there? 0.5. So what did you do? You divided 500 by 1000. So 0.5 liters are there. So like that here, you have 5.5 centimeter cube. So you are dividing that one from 1000. So dividing 1000 you can write by like this, multiplying by 10 to the power minus 3. So that's easier. That's why I'm writing like that. So anyway, so your number of moles of HCl will be 5.5 into 10 to the power minus 6 moles. So where this minus 6 came, here you had a minus 3 also, okay? Yeah, that is just math. Okay. Right, so that is the number of moles of HCl. And since they are reacting in 1:1 ratio, moles of sodium hydroxide, now you can find from that one. So moles of sodium hydroxide in this solution is what? 5.5 into 10 to the power minus 6 moles. Understood? 5.5 into 10 to the power minus 6 moles. So that is the amount of sodium hydroxide available in this solution. Okay, 5.5 into 10 to the power minus 6. Okay, so now it is time for us to discuss about ppm, right? So I didn't said anything about ppm. Just what did I do? Balance the equation, found the moles of HCl, and using the ratio, I found the moles of sodium hydroxide available. So now you know how much sodium hydroxide is there. Now let's express that amount in ppm. So now what is ppm? ppm. So simply you have to memorize this expression. Okay, so composition in ppm is equal to the mass fraction. Let's say here we are considering sodium hydroxide. No? Mass fraction of sodium hydroxide into 10 to the power 6. And as a unit, you are adding ppm. Okay, so you need the mass fraction. So what is mass fraction means? Mass of sodium hydroxide divided by the total mass. You need to remember these facts. Total mass. Total mass of solution. Here is a solution. This is our solution. We need the total mass of that solution. Then multiply by that one by 10 to the power 6. Then you will get the ppm value. Okay, so this is something you are remembering and applying here. So don't depend on the shortcuts or anything. This is the actual theory, no, right? So then use this one. Okay, because I didn't even stress about the short methods and everything. When I'm discussing even your theory class, I focused on this formula because ppm means what? Whatever the mass fraction you have into 10 to the power 6 parts per million. Okay, so this is million, 10 to the power 6. Okay, so here, then you have to write about what is this mass fraction in the terms of the sodium hydroxide solution. Okay, so mass fraction is what? Mass of sodium hydroxide over total mass of the solution. Okay, from this solution, you need to find out how much exactly sodium hydroxide is there. So to find this mass of sodium hydroxide and total mass, now you are going to use this data. Okay, so here I left in a small space to find molar mass. So what is the molar mass of sodium hydroxide? 23 plus 16 plus 1. 40 grams per mole. Now look at this data, okay? You know the moles of sodium hydroxide and you know the molar mass of sodium hydroxide. So by multiplying those two, moles into molar mass, you can find mass of sodium hydroxide. Okay, moles into molar mass. Isn't it? I hope you all can understand that. Then how do you find the mass of total solution? That's where the density and the volume of this one comes. Okay, so density multiplied by volume. That's how you find the mass of the solution. So you need to study this question really well. And like I explained for the earlier question, you should get the ability to explain this one to someone else. Okay, so that means you have learned it properly. Get the idea here. Huh? You need to remember this one. How do you find the mass of sodium hydroxide? So when you are teaching this one to your friend, you have to say, okay, so this is what ppm means. Okay, so mass fraction is this one. And to find the mass of sodium hydroxide, you have to use sodium hydroxide moles and molar mass, multiply them and find the mass, right? And to find the total mass of the solution, you can multiply density and volume and get the total mass, and like that explain. You'll understand and remember this for a long time and practice more questions. It's enough, no? Right? Okay, so how do you find the mass of sodium hydroxide? Mass of NaOH. You have 5 point. Okay, I think it is better to simplify here, right here, because as I remember, it is going to get cancelled. In MCQs, you can follow those tricks. So anyway, 5.5 into 10 to the power minus 6 moles into 40 grams per mole. So here you can see answer will be given in grams, okay? Mole to per mole get cancelled. And total mass of the solution, 1.1 gram per cubic centimeter is the density, and volume 5 cubic centimeters. Now don't convert this one, right? Because why? Because I need to cancel per centimeter to centimeter cube. Okay, so don't convert this into decimeter cube. Okay, you have to think about the units. That's the thing. Huh? If the unit is given in grams per decimeter cube, then convert. Okay, you will understand. So then anyway, you will see all the units get cancelled. Okay, and ppm is the only symbol that is going to remain. Okay, now you can simplify this. Why did I use in this way? Because you can see 1.1 and 5.5 can be cancelled. And this 5 and this 5 can also get cancelled. And this 10 to the power minus 6 and 10 to the power 6 can also get cancelled. Okay, so what is the only thing remain? 40. So answer is 40 parts per million. 40 parts per million. Okay, Lama. Remember this question. Okay, so what are the steps? If you quickly remind again, first of all, find the balanced chemical equation, then find the moles and go to the use the ratio and go to the moles of sodium hydroxide. Then remind what is meant by ppm, and ppm is simply what? Mass fraction into 10 to the power 6. So then you find the mass fraction of sodium hydroxide and multiply that one by 10 to the power 6. And this question is really important. Why? Because when you find the mass of sodium hydroxide, you are multiplying moles into molar mass. That's okay. No, you can do that. But remember, when you want to find the, here it should be the total mass of the solution. Okay, so for that, you must use what? Density and the solution volume. Density into volume. Okay, so dV. Remember density, what was the formula? Density equal mass of the total mass over total volume. Okay, so if you need the total mass, so simply multiply density by volume. Can I understand this only? Okay, follow my advice, okay, trust me. Okay, I'm not doing this one to make myself get any practice. Okay, so I know what to do and how to do. So just follow my advice. You will be able to get a very good A. Okay, so do what we say. It's my only advice, because we are not doing anything forcefully. Huh? We are not punishing you, right? Okay, so it's actually no point of punishing, because why? You are A-level students now. You should understand the the importance and value what you get after doing these things really well, because as a person that is that get the benefit of this one. Okay, I know, so do it. Right, now let's go to this 14th MCQ. So we did a really good 2 chemical calculations, and there's another one coming. Yeah, as a redox balancing is also there. So it's a good discussion for the calculations today. Okay, right. And the next 2 questions, yeah, the next question especially, last week also I mentioned this one. We discussed about the de Broglie equation. No, we discussed about the Planck equation in our first 10 MCQ discussion. And de Broglie equation is another one that is there in chemical. Sorry, that is there in unit 1. What is unit 1? Atomic structure. Okay, atomic structure. So now let's discuss about this de Broglie equation question. So Louis de Broglie is the one who explained the dual nature, wave particle dual nature. Okay, so Einstein said earlier, waves can behave as particles. Okay, or waves, or you can say simply electromagnetic radiation can behave as particles. So he named this energy, particle of energy, or simply he named this one as photon. Okay, so Einstein is the one who explained the particle nature of waves. And Louis de Broglie, using Einstein theories and Planck equation, he kind of explained and showed, okay, the wave nature of particles. Wave nature of particles. Okay, so what was the first thing? Einstein explained that waves can behave as particles. Okay, waves can behave as particles. So Einstein Einstein, and the word photon is the one he used for this one. And Louis de Broglie explains particles can behave as waves. This is explained by de Broglie. Okay, so simply you can now, after telling this one, de Broglie said wave particle dual behavior. Wave particle dual, he called this one as wave particle dual behavior. That means what? Simply any particle that exists in universe can behave as a wave. Okay, so that kind of scary, no? So when we think about ourselves, simply we are also a collection of particles, right? So that means we can also behave as waves. Huh? So we will, as a thing, as ourselves, we'll have a wavelength, right? Okay, isn't it something like that? Okay, so any particle can behave as a wave, and the other thing is what? Okay, and any wave can behave like a particle. So wave particle dual behavior. Okay, so then one important thing I have to tell you, because the thing is particles, any particle like de Broglie suggested, will have a wavelength. Any matter, any object will have this wavelength, wave nature. Okay, wave nature. But the thing is, as the that object or the particle is, if it is getting bigger and bigger, that wave behavior, wave nature will kind of becoming negligible, or it kind of disappearing. Understand? So if you consider a small, very small particle like electron, proton, and those nuclides, right? So they will have wave particle dual behavior at a considerable level. That means those electron will have a considerable wave nature. Okay, but if you consider something like baseball or something, which is a macroscopic object, it's a very large object compared to electron, right? So it will have a negligible wave character, which you can't even find. Okay, so then don't worry. I said earlier, as ourselves can behave as waves, but it is not going to be an observable one. Okay, so that's the idea. So understood now? So what is this de Broglie equation? De Broglie said that any particle wavelength can be found using this formula h over mv. Okay, h is our Planck constant, which is 6.626 into 10 to the power minus 34 joule seconds. This will be given in A-level paper, don't worry. And this is the mass of that object, and this is the speed of that object. So simply, it will give you the momentum, no? Actually, according to physics, momentum is a vector quantity, and this must be velocity. But as a sense, we can, if you ignore the direction, right? So simply, it's kind of showing you the particle nature, no? And this is what? This is a wave character. This is wavelength. So now you can see in single equation, right? Wave characters and particle characters are related. So this is simple. Very, if you simply say to someone, you can explain, okay, look at this equation. Huh? In this equation, you have a wavelength, which is a wave character, and then you have a momentum or mass or into speed, which is a particle character. Okay, so then you can easily explain wave and particle natures are related. So wave particle dual behavior. Okay, so see, it's a simple way, okay, very crude way you can say that. Right, so anyway, what they are asking here is what? This is mass, erase that, no? And this is speed. Okay, so now let's see the question. Now you got an idea about de Broglie equation and what he said as a theory. Look at this. If the de Broglie wavelength of an electron, now electron is, like I said earlier, it's a very small particle which has a considerable or the considerable wavelength compared to its size. Okay, but like I said earlier, baseball will also have a de Broglie wavelength, but it is very negligible when compared to its size. So when baseball is moving, when a baseball is moving, you will not see that wave character. Okay, right. So look at this one. If the de Broglie wavelength of an electron is 200 picometers, what is Pn? Picometers. Okay, the speed of the electron is, okay, so they have given the Planck constant is a simplified value, no, 6.6 only, and mass of electron 9.11. Okay, so let me write those data. So there is an electron which is moving in, let's say v speed. Okay, we don't know the value, and its wavelength is 200 picometers, and its mass is 9.11 into 10 to the power minus 28 grams. Minus 28 grams. Okay. Okay, so now a simple substitution, no? Simple substitution. So if you want to find the speed, what you should do? Subject speed, and that is going to be h over m lambda. But still, you can, some students can get question wrong. Can you understand? This some students still may got this question wrong. Why? Because of the units they have given. You need to have a very clear idea in which units you need to substitute these entities. Now, for example, there'll be no problem with the h, Planck constant. They have given 6.6 into 10 to the power minus 34 joule seconds. It is already in SI units. What are SI units? You know, standard international units. So it's given in joule seconds. So then look at this mass. It should be given in what? What is the SI unit of mass? Should be given in kilograms. Okay, but they have given it in grams. So you need to convert that into kilograms. So how do we convert this into kilogram? By dividing from 1000. Or you can write 9.11 into 10 to the power minus 28 into minus 3 kilograms. So if you simplify it further, it will be 9.11 into 10 to the power minus 31 kilograms. Did you get that one? So that's the value you need to add here. In kilograms. Okay, and then what about the lambda wavelength? Wavelength is given in picometers. So picometer is 1 into 10 to the power minus 12 meters. So it is 200 into 10 to the power minus 12 meters. So if you little bit simplify, it is 2 into 10 to the power minus 10 meters. So these simplifications, maths abilities also will be there. Okay, so 2 into 10 to the power minus 10 meters. Right. Now you can simplify and find. Okay, before do that one, let me make sure you understand that you must apply. Why should we apply these units in SI units? Okay, so let me show you. Because here we are expecting the speed to be meters per second. Okay, so then check this. So check this simplification. Okay, so joule per second, joule seconds, kilograms, and meters. Now let's simplify this. And if you simplify the units, you must get what? Meters per second. Do that and see. Then if it is getting, if the simplification is giving you meters per second, then your then the applying SI units is correct here. Okay, so now let's prove that one. Okay, prove that one. So joules are Newton meters over kilogram into meters. Now you can cut this meters, no? So Newton meters, and there's a second here, okay? Second. And newtons are what? You know F equal ma formula. That's what I remember. Okay, so here it is Newton, no? So it is measured in kilogram and acceleration is meters per square second. Kg ms minus 2. Kg ms minus 2 into S, that's S here, and kilogram. So now kilogram to kilogram can get cancelled and meters per second will be there. Okay, so this is the unit that we expected. So applying SI unit is a must thing for this question. Okay, so you can't get a proper answer by keeping grams. You must convert that into kilograms. And in the same way, you must convert the picometers into meters. So most of the students are converting picometers into meters. I know because we practice that enough. No? But some of you might not convert the grams into kilogram. They might thought that it is not needed. Okay, but you can see after unit simplification, it is a must thing, right? You must convert, it into kilograms. So now get a proper idea. Time to time, they can check this one in exam. So you have to be prepared. Okay, so it's a good theory. Just understand anyway. Not only for the A levels. Anyway, if you're learning further, you must get the proper idea. Why do we do such things? Why do we apply units? What is the importance? This is the importance, Lama. Because if you didn't use proper units, you will get a false answers. Okay, right. Now let's simplify this one and see. Now for this also what I'm recommending is don't go into an actual simplification. Why? Because it is 9.11. You can see it is not divisible. Right? So it's going to be a very huge problem for you. So just round off. So take this as 6.6 and take this as 9 and take this as 2. And then simplify the powers separately. 10 to the power minus 34. Here you will have 10 to the power minus 41. Okay, so if you simplify, this will give you 10 to the power 6 and 1, 7. 10 to the power 7. Yeah, 10 to the power 7. And here 3.3. And you can divide this one again. 1.1 over 3. 1.1 over 3. So simply somewhere around 3 point something. Yeah, 0.3. 3 point something into 10 to the power 6. Okay, 10 to the power 6. Now check your answers that they have given in the paper. Then you can come to a conclusion. So what's the proper one? 3 point something is there in 1, 2, and 3 answers. So 10 to the power 6 is available only in the second answer. So answer should be answer 2. Okay, so those are small tricks for you to do in MCQ papers. I know by now you know all these things because we practice enough questions, right? So when we do MCQs, especially like this, we are not going to simplify using actual values. So we round off and compare the given answer, compare with the given answers. Okay, so what is the summary of this question? What's the summary of this question? So first of all, you need to remember the de Broglie equation. That's a must thing for this question. And then subject the speed. Okay, that's what they're asking. And make sure you apply the data in SI units. Okay, so explain in your review why we must use SI units. Because if you use only these SI units, you will get the answer in meters per second. Okay, so do it and understand. And finally, you need to round off to get the answer quickly. Okay, so I hope that is clear. Okay, then look at this one, 15th question. 15th question. Right, this is from gaseous state lesson. Okay, gaseous state lesson. So they are asking the Maxwell-Boltzmann speed distribution of 4 gases is given below. Okay, so A, B, C, D. There are 4 gases. And they're asking which is the proper order of these gases. That means their examples are given in answers. So you need to select the correct combination. Okay. So I'll explain a little bit about the Boltzmann curve and how to get this answer. Okay. Right. So here's the idea. Here's the idea. So listen carefully and try to understand. Okay. Right. So it's about gases. You need to change the track. Right. So gases in kinetic molecular theory. In kinetic molecular theory, we are telling, okay, so it's a property for gas molecules, right? They are moving in random directions. Random directions in straight lines, and in different speeds. Remember this point? Different speeds. So if it is an ideal gas, okay, or even a real gas doing this one, they move in random directions in different speeds. Okay, random straight line motion in different speeds. That was the sentence in our tute. Okay, what is that? Random straight line motion in different speeds. So different speeds is a very important thing it's a good place to start the discussion. Different speeds. So that means a gas sample, gas molecules, even an ideal gas sample, will have different speeds for their molecules. Understand? Will have different speeds for their molecules. Okay, different speeds. Okay, so the meaning. What's the meaning? Different speeds. So we can explain that their speeds are different by using this Maxwell-Boltzmann speed distribution. So in that graph, right, in the x-axis you have speed. So it's a different thing than what you do in physics. In physics, usually in x-axis you have time or something. In the y-axis you have this speed. But here in chemistry, be careful. In x-axis you have speed in this graph. So what is there in y-axis then? You have fraction of molecules. Fraction of molecules. You have fraction of molecules. Okay, fraction of molecules. So then the graph will look like this. It's an asymmetrical graph. It's not symmetrical. It's an asymmetrical graph, and you can see gas molecules are having different speeds. So that's prove this different speed point. Understood? Different speed. They are having different speeds. So now you can see some fraction of molecules are having lower speeds. And there is a fraction of molecules that are having higher speeds, but that fraction is low. Okay, now what you can see from this Boltzmann curve is the fraction of molecules having lower speeds are low, higher speeds are also low. You can see a majority of gas molecules of the ideal gas sample will have moderate speeds. Moderate, so that means some in between, not higher, not lower, moderate speeds. Okay, so this is, you can see this special place is there, which is having the highest fraction, the speed shown by the highest fraction of molecules. Okay, but again, the speed shown by the highest fraction of molecules. So you need to be able to read a graph. See how it is going? The speed that is shown by highest fraction of molecules. Okay, so we call that one as the most probable speeds. Most probable speeds. Okay, so in other words, we put a symbol CMP, most probable speed. Understood? So this is simply the Boltzmann curve. And what the first theory point is what? Remembering this point from kinetic molecular theory, and then remembering the Boltzmann curve and getting this most probable speed idea. And actually this Boltzmann curve explains the different speed thing. It's a full theory discussion, okay, I'm doing. And then the next point, this whatever the speed they are having, speed of gas molecules, whatever the speed, there are several types of speed for the gases, no? Remember, what are the types of speed? You have this most probable speed. So if now this graph suggests that they are having different speeds. Then if, for the sample, you may need to get an average speed. Okay, so then you have average speed, which we symbolize by C bar. You have CMP, most probable speed, average speed, and there is something other one called C square bar root. Root means square speed. So this is necessary to get the formula for the average kinetic energy of one gas molecule. So I'll explain how this is coming in our structured essay discussion. Okay, but anyway, my point is there are different types of speeds defined for a gas sample. Different types of speeds are defined for the gas sample. Understood? So, but any of these speed will be directly proportional to T over capital M root. What is this T? T is your absolute temperature. Okay, capital M is the molar mass. So T over capital M root, it is proportional to, direct proportional to whatever this speed. There are different formulas for these speeds, which you can find those in your theory too, but no need to remember them. Just understand, any of those speeds will be directly proportional to what? It will be directly proportional to the T over capital M root, temperature over molar mass root. Okay, so understand that really well. Remember that one. Okay, so then simply you can get the relationship here. So remember our question. So it says something about the temperature. No, let's go and see. Yeah, it is telling we do this one at 300 Kelvin. 300 Kelvin. So that's a certain temperature. No? So temperature is constant. So if temperature is constant, you can say speed will be inversely proportional to what? Root of the molar mass. So simply what you can understand, don't do any calculation here, okay? It's not a question that you have to use calculations. So simply you have to look at the molecules and understand, okay? So simply what you can understand is this is statement. If the molar mass is higher, that means if this is higher, what will be happening? The CMP, or you can simply say speed, is lower. Understand this statement. Okay, speed will be lower. Right now, what are the four gases they have given? Again, let's go to the question and see. They have given H2, N2, N2, O2, and Cl2. These are the four gases. Right, so they haven't given molar masses, but actually you don't need the molar masses. You can just approximately understand. This is the lightest gas, then N2, then O2, and this is the heaviest gas. Okay, because chlorine is atomic number 17. So 17 means at least, it should be heavy. There are 2 chlorine atoms here. Okay, so the relative molecular masses or molar masses of this one is 2. This one is 14 plus 14, 28. This one is 16 plus 16, 32. This one is 71, 35.5 into 2. Now you can see this is the heaviest one. Then chlorine is the one that is having the lowest speed, lowest CMP. And this should be the one that is having highest CMP. Now you can check our graph. And be careful, like I said earlier, speed is there in what? X-axis. Okay, so now let me finish that one by drawing another Boltzmann curve. Another Boltzmann curve. So let's say, if you consider these two Boltzmann curves, which one is having the lower speed? Lower speed one is this. This is the one with lower CMP. This is the one with higher CMP. Look at the graph. Okay, so then what should be the Cl2? This should be Cl2 and this should be H2. Understood. So H2 should have a higher speed. And then if I talk about little bit about the wave, about the area under the curve should be same because we are the area under the curve representing the 100%. Okay, so because this is the fraction, so area under the curve should be same. So if the speed is increasing, graph should shift to the right side. While it is shifting, the maximum point should get a little bit lower. Okay. Right now, what is the answer? If you consider A, B, C, D graphs. So the one with the highest speed is given by the graph D. You can see the CMP will be highest for the D gas. So then D gas should be H2. Okay, and what should be your A gas? A is the lowest speed gas, which is Cl2. So your answer should start from Cl2. There's only one answer that starts from Cl2, which is this one. Understood? So your answer is going to be answer 2. That's how you get that. Is that clear to you, Ramay? Huh? Understood that? Okay, so what are the theory points? If I summarize again this question, how do you find the answer? Just understand first of all the kinetic molecular theory. According to kinetic molecular theory, gas molecules are moving in random straight line motion in different speeds. Okay, so this different speed can be nicely explained by Boltzmann curve. Okay, according to the Boltzmann curve, you can see gas molecules are having different speeds. Okay, and in the Boltzmann curve, there's a maximum point. The speed relevant to that maximum point is called the most probable speed. Most probable speed. Okay, and this most probable speed or whatever the speed, there are several types of speeds, and all those speeds are depending on T over capital M root. They are proportional to T over capital M root, directly proportional, right? And if the temperature is constant, like it says in this question, speed will be inversely proportional to the molar mass. That simply means this is statements. If your molar mass is higher, okay, speed will be lower. So the highest molar mass gas is Cl2. That means the lowest speed gas should be Cl2. So Cl2 is the one that should be there to the leftmost CMP. Okay, so then if you check the graph, okay, it should be gas A. Okay, so A should be Cl2, and there is only one answer that start from Cl2, which is your answer 2. Okay, so that's how you find the answer. Okay, so I hope you understood these 5 questions really well.